Okay, everyone, open your book to page 295. We're going to work on question number 21 here, and here's what we're going to do. I'd like you to first find the velocity function. I'd like you to find the position and velocity at time t equals 1. I'd like you to answer at what time the particle is stopped, and that's it, okay? We're going to do the green part here, and then I'm going to talk about yellow in a second, all right? Don't look at my work over here. I already started it. But what I'd like you to find for part A and for B and C is I want you to find, given the position function here, please find the velocity function. Find the critical points of velocity. In other words, where will velocity equal 0 or where will velocity be undefined? And then you're going to do a sign analysis on velocity to see when the particle is moving right and moving left, okay? That's what I'd like you to do right now, and then replay me. All right, here's my work, and you'll see is everything with calculus. A lot of it's the algebra, but this part, nothing new here. V is the derivative. Being careful I use the product rule correctly. Then here's what I did with v of t. Knowing that I have to work with v of t, I took out the constant factor of e to the negative t over 3. That's right here. And what's left inside is 2t minus 1/3 the quantity t squared plus 8. I then set velocity equal to 0. There are no points where v is undefined. Set the velocity equal to 0. This factor here will never equal 0. It will always be positive. The question is, when will this factor equal 0? And this is a quadratic equation. Now look what I did over here. I factored out a negative 1/3 out of this, okay, out of that quadratic factor, which is all fine. I have to just make sure I keep track of it. There's a negative 1/3 factored out, and there's an e to the negative t over 3 factored out. If you want to think of it this way, you can think of it as me factoring out negative 1/3 e to the negative t over 3. So now this factor is always going to be negative, right? Okay, and the reason why I factored negative 1/3 out, or you can think of it this way, I multiplied both sides of this equation by negative 3, same idea, is because if I look at this now, it's lovely and beautifully factored. At time t equals 2 and t equals 4, v of t equals 0. Now here's my velocity number line. It should resemble something to you. Yes, the f prime number line. 2 and 4 at times t equals 2 and t equals 4, v equals 0. That means at times t equals 2 seconds and 4 seconds, at those moments, the particle is at rest at those moments. And then I just did a straight up sign analysis here. Being careful to recognize that, when I'm here, don't forget about all the things we factored out of velocity. Negative 1/3 e to the negative t over 3, and then I have t minus 4 times t minus 2. Okay, just don't forget that we factored out the negative 1/3 e to the negative t over 3. So velocity is negative, positive, negative. That means particle is moving left here, particle is moving right here, particle is moving left. Okay? Here's what I want to talk about right now. Let's see. The question here asks us to find the velocity and position at time t equals 1. Well, let's do that right now. At time t equals 1, that means v of 1 equals, I'm just going to use the velocity function right here, negative 1/3 e to the negative 1/3 times negative 3 times negative 1, or I get negative 1 e to the negative 1/3. Okay? Just for the purposes of this screencast, I'm actually going to find out what this is approximately equal to. Okay, so at time t equals 1, the velocity is approximately negative 0.717 feet per second. Okay, let's talk about this for a minute. At time t equals 1, which is right between 0 and 2, obviously, the velocity is negative 0.717 feet per second. If I were to ask you what this number means in the context of this situation, I hope you'd say that at t equals 1, the particle is moving left, okay, at a speed of 0.717 feet per second. Notice what I don't say. I don't say moving left at a speed of negative 0.717 feet per second, because the negative here is implied in the moving left, all right? If I said moving left at a speed of negative 0.717, that would actually mean it's moving right. So it's important that when we write down what this means in words, that the left is implied in the sign. So now I'm going to get to what you think the relationship is between velocity and speed. Velocity indicates direction because it could be positive or negative. If the velocity is negative, that means it's moving left or down. If the velocity is positive, it means it's moving right or up. Speed, on the other hand, pays no mind. It does not care about direction. So speed is the absolute value of velocity. Okay, speed is the absolute value of velocity. Speed pays no mind to direction. So please make a note in your notes. We've just talked about speed. All right. A couple things to go over here before I go into the next thing is I want to talk about when we talk about whether the particle is moving right or moving left. I know we said in class that the particle is moving left over the interval of time from 0 to 2 and 4 to positive infinity. I don't think it has an end time, right? Okay. And it's moving right over the interval of time from 2 to 4. There are some out there who will say, no, this is so confusing. That means at times t equals 2, the particle is actually moving both right and left. I mean, yes, one can look at this notation and think that, but you have to know also that inclusive intervals is just by definition, and that when we glean meaning about what's happening at time t equals 2, you have to take into context or take into account the entirety of this work, and we know already that at times t equals 2 and 4, the particle is at rest, right? So even though, yes, notationally it's inclusive, we understand what this means, okay? All right, let's talk about a very important idea, which is the difference between distance traveled versus displacement. Okay? And here are two very easy ideas. Let's say this is you. Okay? This is you. And let's say you move 5 miles to the right, and then you travel 5 miles left. Your distance traveled is 10 miles. Okay? Displacement in that situation is your ending position minus your initial position. And in that case, in this situation where you have that mohawk and you run 5 miles right and 5 miles left, your displacement would equal 0 miles. Okay? Now, when does it matter? When will distance traveled and displacement be the same number? Well, in the event that you are traveling and you never change direction, then your displacement will equal distance traveled. Am I right? Let's see. If I say I start here and I run 40 miles to the right, I never change direction. Ending position 40 minus starting position 0 will be 40. The only time you have to be careful of is that distance traveled, when someone asks you about distance traveled, this is always a positive entity. It's always positive. Okay? So in this case, let's take this example of this person here. Let's start over. New person. Okay? Let's say you begin and your position at time t equals 0, your position is -1. And I travel this way, and I end, my position here is -38, okay? Distance traveled, it's going to be, if I've never changed direction, end position minus beginning position, or in this case, -38 minus -1, which equals -37. But that's an odd thing to say when someone asks you for distance traveled. Really, when they ask you for your distance traveled, they just want to hear that you ran 37 miles. Okay? Displacement, though, displacement gives a little more information in that, in this case, if you started at -1, and I realize my negative kind of got eaten by the equal sign. If you start at -1 and you run -38, or you end at -38, your displacement here is going to be negative 37. We keep the negative with displacement because this tells me that you ended, your ending position, right, was 37 units left of your starting position, right? So displacement is, we like to keep the answer. If the answer is negative, we like to keep the negative. But distance traveled, you generally want to keep that entity as a positive entity. When someone asks you how many miles you ran, you don't really necessarily want to hear, well, I ran negative 11 miles. You just want to hear you ran 11 miles, okay? Displacement is just end position minus initial position. Which then brings me to the question over here about this little particle, okay? We want to find the total distance traveled by the particle from time t equals 0 to time t equals 5. So I'm just going to put on this number line, like here was time t equals 0, right? And time t equals 5 is right here somewhere. And I want to find the total distance traveled. Well, let's go up a notch and let's find particles, this particle's displacement and the total distance traveled. So let's say we're going to find displacement over the interval of time from 0 to 5, and also distance traveled over the interval of time from 0 to 5. Okay, go ahead, you do that first, and let's see if you can replay me. Maybe you're working with someone here, but distance traveled, you want to take into account all these changes in position. Okay, go ahead and think it through, then replay me. Okay, displacement's easy, right? Displacement from 0 to 5 is just the position at 5, end time, minus position at 0, beginning time. And you just plug in 5 and 0 into the position function, and we get this. Without a calculator, you leave it like that. Distance traveled is going to be a little bit more interesting. So here's what I did. Look at the position values I needed to find. Why did I have to do that? Because the particle changes direction at 2 and at 4. And so I made this little note to myself. I need to find the position at these times. And look what I did here. I just said between 0 and 2, the particle is moving left. So to find the total distance traveled between time 0 and time t equals 2, I took the rightmost position minus the leftmost position, since the particle is moving left. So this is the distance traveled, total distance traveled between 0 and 2. But now look at the time from time 2 to 4. The particle's moving right, so the rightmost position is going to be this one, the rightmost position minus the leftmost position between 2 and 4 seconds, right? And then the particle's moving left from 4 to 5. I'm looking at the rightmost position, because it's moving left, remember, at 4 seconds minus the position at 5 seconds. These are the distances traveled over the intervals 0 to 2 seconds, 2 to 4, and 4 to 5. And what do you think you would do with these to find the total distance traveled? Add these all. Add for total distance traveled, okay, over the interval of time from 0 to 5. And when you add these up, you get this. I'm trying to do it on the fly here. Add these all up, we get 8 minus 24e to the negative 2/3 plus 48e to the negative 4/3 minus 33e to the negative 5/3. This is your total distance traveled. And I kind of like just the very easy mental math here of thinking about, oh, what do you subtract from the other one? Which one do you subtract from what, right? You pick the higher position minus the lower position. And what's higher or lower is going to depend on whether the particle is moving left or right over that interval of time. So let's just make sure we're clear here. So what we talked about in this part of the screencast, the new ideas here is speed, okay, versus total distance. We did a curve analysis in terms of the sign of V, right, which tells us whether the particle is moving left or moving right. I'm now going to go right into acceleration for this screencast, okay? So as you can imagine, if you think about the units, let's just talk about this for a second. If the units of position, let's say, are feet, The units of velocity are going to be, let's just choose feet per second, since that was the question in number 21. The units of the derivative of velocity then is going to equal feet. Okay, it's going to be feet per second, or feet per second squared. And feet per second squared then is describing acceleration. So if you want to put this all together, in the world of rectilinear motion, the position function is obviously the position function. S prime of t equals v of t, and S prime prime of t, which equals v prime of t, equals the acceleration function. Okay, this is kind of the way things roll in our world of just rectilinear motion. All right, and tomorrow I think what I'm going to talk about is how you could tell if the particle is speeding up or slowing down. Very, very important. What I'd like you to do right now, if you would, is please do. Okay, number 3 on page 294. It's right here. Unless you want to, you can look at it in your book as well. Go ahead and do this one. And I want you to, for right now, if you want to think about speeding up, slowing down, you can. But I'll talk about that tomorrow. But A, B, and D right now, please. And then replay me for the answers. I just realized D is about speeding up and slowing down also. But part A, particles moving left. The most pithy answer is because the velocity at time t naught is negative. If this is the position function, velocity is the slope of the line tangent to the position function. It is clearly negative. Acceleration is negative there because at t naught, you can see that S is concave down. Look at S double is negative. If S double is negative, that means the same thing as A being negative. Okay, let's talk about C right now. I might as well since we're here. Is a particle speeding up or slowing down at time t naught? Okay, here's what I want to tell you. Let's take a look at this information right here. What we just wrote down, or what I wrote down in purple and in this kind of like, someone just walked by my room and said that looks like poop brown. They just called this color poop brown, which I think a little bit mildly offensive. It's not poop brown, it's just brown. At time t, at this time right here, the particle is moving left, okay, which means the velocity is negative. The particle is moving left, the velocity is negative, and look at this. The rate of change of velocity, which is v prime is negative, which is A, right? If v is negative and v prime is negative, so let's take a look at this. V of t naught is negative and v prime of t naught is negative, because after all, v prime and A are the same thing, right? This here is telling you that the velocity is negative and also decreasing, right? This says velocity is decreasing, which means my velocity is negative and getting more negative. So negative 10 miles per hour, negative 20 miles per hour, negative 80 miles per hour. The simple person would say, well, if my velocity is getting more negative, the particle is slowing down. But you are not simple people. If the velocity is negative already and getting more negative, that means the particle is speeding up. So at time t naught, right, at t naught, comma, particle is speeding up. And you can write this down because v of t naught is negative and it is getting more negative. All right? Now, let's take a look at t1. Is the particle speeding up or slowing down at time t1? Let's see. You tell me. If I look at that, v at t1 is clearly negative because the slope of the line tangent to position is negative. Okay? But if I look at that graph right here, I see that that's the part of the function where s is concave up, correct? So A at t1 is positive, right? And don't forget, we know that this means v prime at t1 is positive. So let's take this together. This says the velocity is negative and the velocity is increasing at time t1. The velocity is negative and the velocity is increasing at time t1. That means, say, a negative velocity is increasing. So negative 5 miles per hour then jumps to, say, negative 1 mile per hour. Okay? What's happening here is the velocity is negative and increasing. That means the particle is slowing down. Particle is slowing down. So a couple of things I want to tell you. Right here, we just debunked some layman misconceptions. The layman misconception is, oh, if acceleration is positive, the particle is speeding up. And hopefully you now know that is not the case. It's all about the relationship between acceleration and what? Yes, velocity. A particle is speeding up if A and V have the, what everyone? Beautiful. Particle is speeding up. Particle, what on earth is up with my pens? Particle in rectilinear motion speeds up when A and V, I shouldn't be so careless. Some of you have such beautiful handwriting, and I normally do too, but when V of t and A of t have the same sign, okay? It's not just saying acceleration is positive. If acceleration is positive, the particle is speeding up. No, 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 no. It's also not okay to say that velocity being positive means the particle is speeding up. No, 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 no. Speeding up or slowing down has to do with the relationship between V and A. Okay, you can write the second statement here, particle slows down when V and A have the opposite sign. And so now we are able to do a full motion analysis, okay? What I'd like you to do right now, and I want you to play me, is to do the full thing, the full shebang on, oh, should we do a piecewise? Oh, absolutely, let's do a piecewise, let's see. All right, I'm going to change the instructions here, okay? I want to go to question number 32. If you look at number 32, I want you to do the following. I'm going to write it down, then you're going to do it, and you're going to replay me. Okay, I pulled this function just from question number 32. Here you're given a position function that's defined piecewise, but then I completely changed all the questions to make it a little bit more involved. I want to find when the particle is farthest right over the interval of time from 0 to 5. When is the particle farthest to the right? B, I want you to find when the particle is speeding up. It could be an interval of times when the particle is speeding up. And then I want you to find the maximum speed. Max speed. This is a great question, everyone. Go ahead and try this one and then replay me for all the answers. All right, what a great exercise this is. So, when is the particle farthest right, and when is the particle speeding up? First of all, find when the particle is farthest right over the interval. Guess what that is? Yes, it's an optimization question. Optimization question where you want to optimize or find the max of position, which means working with position prime. So here's my velocity. Look at that. Velocity in two pieces. Velocity in two pieces. Look at my lovely velocity, and then look what I did here. Do you see what I did? I factored out a 2t minus 2 out of these two terms. Look how much easier that makes my life. So much easier, right? The velocity of this piece. What happened here? Oh, goodness. Apologies. I just totally caught a careless mistake. I just caught another one. Oh my goodness, what a big fat mess I made. See, this is the reason why when Missy M just makes up questions, it always becomes this big fat vomit mess. And anyway, so here I am looking at each piece of velocity after I cleaned and cleaned and cleaned, right? And I'm looking at the top piece here, v will equal 0 at time t equals 2 and t equals 2/3. I have to make sure that these 2 and 2/3 fall within the domain of this piece. The bottom piece, v will equal 0 at t equals 4. And I'm again checking to make sure that t equals 4 falls within this domain of that piece, and it does. Now, this is where things get very interesting. I'm going to go over here and do a V sign analysis, okay? And the V sign analysis, here I have 2/3, 2, and 4. Okay, and I just put 3 down here because I'm noticing that at 3, you know, I change function, so to speak. So I'm just curious to see what's happening. And then I plug in values in between these intervals into the V function. I have this, plus minus, plus minus. Okay, now I'm going to go ahead and take the, I'm going to go ahead and take a look at this and say what I've got going on here is this. Oh gosh, I've got to take, what just happened? Okay, I've got to take a look at where is the max position. So I want to make sure we're on the same page. So position, think about this, increases, decreases, increases, decreases. That means there's a potential max at 2/3, max position at 2/3, okay, and a max position at 4. So this is my error that I caught early on. So I have to compare position at 2/3 with position at 4. So this is all, okay. When you go ahead and find position, compare those two numbers, which I know that you can do, and then you're going to say what your final conclusion is. Particle is farthest to the right at whatever time has a larger position, and this is the first derivative test for extrema. All right, on to acceleration. Here's my acceleration. Look what I did. When I took the velocity, I multiplied the velocity all out, knowing that I have to take the derivative, right? When I take that derivative, here's A. A is going to be 12t minus 16. A is going to be negative 14. That's interesting. And I'm looking here at that first piece of the acceleration. A will equal 0 when t equals 4/3. Okay, and I'm noticing that from 3 on, acceleration is always negative. So here's my acceleration number line. Acceleration is negative, neg, from 0 to 4/3. Okay, and then it is positive from 4/3 to 3. Right, and again, I'm plugging in a convenient value for t into this piece, but then from 3 on, I know acceleration is negative. Now, when is the particle speeding up? Well, the particle is speeding up whenever v and a have the same sign. You have to be a little bit careful here because, you know, if your number lines aren't perfect, and I'm noticing here that mine are not, but v and a have the same sign between 2/3 and 4/3. Look at that. From 2/3 to 4/3, A is negative and V is negative. Now, A starts getting positive at 4/3, and V is positive at 2. So that means from 2 to 3, right? Because 2 is bigger than 4/3. So from 2 to 3, the particle is also speeding up. So let's go around here and say particle is speeding up on these following open intervals, on the intervals from 2/3 to 4/3, comma, where else? From 2 to 3, and then also where else? It looks like both are negative again from 4 to 5. 4 to 5. Those are the intervals of time when the particles' velocity and acceleration have the same sign, okay? I want to see what you did with finding the maximum speed over this interval of time. And let me say this, if you were able to follow your way through this question with my modified directions, all this algebra, right, and if you're kind of doing what you should be doing with these screencasts, which is not just playing me, but playing me certainly, but also pausing when I ask you to pause, you guys should be in good shape. All right, homework is going to be the following. All right, here it is, the whole thing. At the start of class tomorrow, I want to see each and every one of these up on the board. I want to see different people. I want to see beautiful work, thorough work, all of it. All right, bye everyone. Have a great night.